ITER 154M, the first in a series of data-driven compositions. Hydrophonics is a series of compositions relating to conditions affecting liquid flow in an enclosed transport system. Familiarity with the mathematical and scientific process is necessary to engage in this type of composition. Accessing the data requires consent for release to use. Eta is a symbol of viscosity. It is used to measure the resistance and flow of a liquid. 154M is the length of the pipeline under investigation in a cooling system. Variations of temperature, irregular volumetric flow rate, fluctuations in kinetic viscosity usually cause wall surface roughness in the cooling process were signs for concern. The pipe was inspected to determine whether there were corrosion constraints leading to head loss complications. This was an on-site project, and work on the composition took approximately 3 years to complete. I will briefly touch on certain scientific areas of importance to shed light on unfamiliar terms, types of flow mechanics, flow resistance, on how data was used in the final score. Flow mechanics. When fluids flow, they have a certain amount of interior friction called viscosity. This is a force between different layers of fluid as they move past one another. In liquids, the viscosity is due to the cohesive forces between the molecules. Due to adhesive, cohesive and frictional forces, a velocity gradient exists. The magnitude of this gradient is how fast the speed changes with distance. Isolating factors controlling how fast liquids flow through the pipes depend on the pressure difference between the ends of the pipe. In other words, the bigger this difference, the faster will be the flow. More liquid will flow through a shorter than a longer pipe in the same time. Also, more liquid will flow through a wide than a narrow pipe in the same time, taking into consideration the radius of the pipe. Two flow systems: laminar flow and turbulent flow. Laminar flow exists in Newtonian fluids. A streamline is an imaginary line with no flow normal to it, only along it. When the flow is laminar, the streamlines are parallel and flow is made up of parallel laminar layers. In a pipe, these laminar layers are cylindrical and may be called stream tubes, as you can see from the diagram above. In laminar flow, no mixing occurs between adjacent layers and occurs at low average velocities, A compared to B, and as we can see from A to B, that is the flow pattern followed. In a non-viscous fluid, the pressure drops with the tube narrows and average velocity increases. In viscous fluids, additional pressure drops occur due to the work done against viscous frictional forces. It is important to identify and define three factors. First, the friction coefficient calculates the pressure drop in the pipe. So the friction coefficient is equal to the wall shear stress divided by the dynamic pressure. The dynamic pressure, for instance, Consider a fluid flowing with a mean velocity. If the kinetic energy of the fluid is converted into flow or fluid energy, the pressure would increase. The pressure rise due to the conversion is called the dynamic pressure. Relative surface roughness is defined as mean surface roughness multiplied by the bore diameter. Thus, in cooling systems in industry, it is important under ideal conditions to have laminar flow. Let's observe the diagram above. Y is a distance above the solid surface. L is the arbitrary distance from the point upstream. dy is the thickness of each layer. dl is the length of the layer. dx is the distance moved by each layer relative to one below in a corresponding time, dt. u is the velocity of any layer. du is the increase in velocity between two adjacent layers. Each layer moves a distance dx in time, dt relative to the layer below it. The ratio dx over dt must be the change in velocity between the layers, so du equals dx versus dt. In other words, the distance moved by each layer relative to one below in a corresponding time. Turbulent flow exists in non-Newtonian fluids. It does not obey Poisson's law because the viscosities are velocity dependent. In other words, if it did obey it, the viscosities would be velocity independent. If turbulence does occur in the flow, then the volume flow rate is dramatically reduced. A pipe with uneven or rough surface areas promotes various degrees of turbulence because the wall shear stress is the shear stress in the layers of the fluid next to the wall of the pipe. You can see from the diagram above, I downloaded this diagram just to show you the variations in viscosity between an oil, water, and air, and the blood and plasma. We can see as temperature increases, the oil viscosity drops dramatically from 5.3 to 0.986. Water differs. Air increases in viscosity as temperature increases, and normal blood and blood plasma decreases in viscosity as temperature increases. Here is the cross-section outlay of the pharmaceutical cooling system. Pipe diagnostics, total length of 154 meters. This is a diagrammatic representation of the system consisting of difference in pipe diameters, 8 millimeters, 13 millimeters, 3 millimeters, and 13 millimeters as it varies around the system needed to be cooled. As you can see, Fy, Fz, and then the A, B, C, D, E flows with the round circles which represent valves in the system. There, the outflow The cross-section piping size remains the same, but the walls of the piping become thicker as the diameter decreases. This is to keep temperature constant within the desired specifications. Let us say that the dimensions of the pipe are within the required specifications. Then the focus will be on factors affecting viscosity other than temperature, such as pressure, wall roughness, and corrosion. However, with corrosion we could get thinning of the pipe wall that could result in fluctuations in temperature to the system. Here is the geometric dimensions of the pipe, the different angles. And this is the actual pharmaceutical cooling system that needed to be replaced. Corrosion detector used with multi-mode acoustic signals, generates and receives using simple single element sensors. Changes in energy distribution over the selective modes are analyzed through signal processing to monitor material loss or addition. Corrosion effects such as pipe wall losses or solid material deposits in the pipes are simulated numerically. To reduce errors in the measurement due to changes in local or global temperature of the measured media, a universal temperature compensation algorithm is introduced. This, in other words, reduces spurious temperature effects on the measurement technique by 10 to 100-fold, while not significantly interfering with the detection of mechanical changes. This detector is used in structures that support specific acoustic modes of guided wave propagation, and a careful interpretation of the propagation modes is required. The signal recognizes distinct areas from known structural features such as the ends of the pipe, welded joints, stands, clamps, and also unknown structural features such as corrosion. A cross-section through the pipe where the transducer is connected to the top of the pipe, and an analytical wave travels around the circumference of the pipe. If corrosion is detected, the frequency of the wave changes appropriately. The diagram illustrates the outcome results compiled from 8 cross-section locations in the clockwise direction of the pipe under investigation. The corrosion detected in the walls of the pipe. Optical diagrams representing schematic morphology of corrosion prepared on transverse sections. The types and shapes of corrosions detected. The examining device determining flow gave precise calculations of structures and types of corrosion in specified areas. A. Penetrable corrosion, B. Impenetrable corrosion, and C. Suspended in fluid. Dislodged corroded particles such as between figures 6A1 to 6A3. A sound wave is a continuous wave and is a mathematical curve that describes a smooth periodic oscillation, a concept developed by French mathematician Joseph Fourier to describe smooth repetitive oscillations. Our base eta 154m on the absolute value determined by scientific data, which prompted generation of sound waves from data recorded in MATLAB. The waves are integral to the entire sound and are still capable of precisely addressing data. This is a primary sound wave that would be introduced into the tube. The engineers supplied a cross-section partition results of analytical data such as pressure, density, frequency, viscosity with respect to length from every section investigated along the 154 meter of the pipe. Viscosity calculated from the above results was directly proportional to the flow rate. Frequency changes of the sound wave are directly proportional to the surface roughness and viscosity. Here is a frequency de-escalating and then escalating. Plot variations in pressure, viscosity, frequency with respect to laminar flow, as seen on the diagram above. There you are. Pressure, viscosity, and frequency. Along 33 meters to 35 meters in length of the pipe. Plot variations in pressure, viscosity, frequency with respect to turbulent flow. You can see the variations, how intense the frequency changes. You can see the frequency changing on the light green levels as viscosity increases and decreases, and the pressure increases and decreases. These are frequency results from 8 partitions detecting corrosion. So from one section, 8 partitions, the readings from 8 partitions, in other words 13 particular readings were taken. This is detecting corrosion at 12.56 meters, and this is the graph plotted, which shows the overlaps. As you can see, there's areas of overlapping, intense overlapping, which could create problems with the sound. This is 3.7 meters of the pipe, various readings taken through each partition, each of the 8 partitions, also showing overlaps. Readings from the 8 partitions selected are converted to sound waves and frequencies provided. The sound waves are then superimposed on each other, producing complex acoustic results. However, the disadvantage is that in certain cases the acoustic complexity was overpowered. Data was graphically plotted and inspected. The areas of the graph showing overlapping frequencies that were affecting clarity of the sound, these sound areas were then rearranged into a linear trajectory. A frequency plot showing minimal resistance. Area shows quite a bit of resistance due to viscosity. In summary, the capturing of data was repeated to exclude errors. Transcription of data was used to plot comparative frequency, pressure, viscosity flow graphs, determining areas of surface roughness. The plotting of graphs helped to identify areas where sound would be compromised. This helped restructure and reposition the sound files. All calculations and algorithms were generated through MATLAB software. Inspections of complex waves were done using Fourier acoustic analysis. The escalation of frequency detects corrosion buildup and extension from the wall, and the de-escalation of frequency detects corrosion in the walls of a pipe. The composition is broken down into 13 sound blocks, showing pitch variations, revealing moments of laminar and turbulent flow in areas with surface roughness on a macro and micro environmental scale. Hello, Theo.
Hi, Dimitri. Fascinating stuff. I was about to type, please leave questions to Mr. Voudouris in the chat, but I'm sure we can chat and the chat will chat back.
Sure.
I've got a gazillion questions here. So from a person, so from my perspective, I'm not embedded in the thought process and the thought processes underlying this composition. So you have to excuse me for maybe putting slightly uninformed questions. But just as a starting point, if I as a musician who's into technology hear pipe, flow, viscosity, etc., the first thing I think of is a delay line, like a reverb unit.
Exactly.
But you've relied on data taken from measurements in a physical pipe that is part of a cooling system. You've relied on data taken intermittently at points in this pipe to generate sound. Is that correct?
That's correct. That's correct, Theo. It's as you see, the indication of the pipe, the circular pipe. It was divided in 8 different layers. So there was data given to me on each of the 8 layers where the corrosion was detected.
I see.
So I had to diagram. That's why it took me three years to complete this.
Good for
it
you.
was an enormous task,
Yeah.
Yes, I've got a whole bunch of notes like that from data. So, okay. So from a circular path, okay, 8 different positions. So 8 different stories told and given to me, and I had to convert them into sound data, and then I had to put graphs together to see where the actual where the graphs would go over each other, and then they would, for instance, be to the deficit of the sound. So I would have to listen to them and then decide, okay, is it clear to the audience, or should I create extra layers to show the actual happenings in the sound? So that was the complete arrangement of the composition, step by step.
Right.
Yeah.
Right. You see, where I had it wrong initially, I thought we're talking about 8 cross sections through this pipe, but what you're actually talking about are layers within the pipe, that data derived from those layers.
You're right, Theo. There are cross sections. The analysis is on cross sections, but say for instance, in a clockwise direction, like a clock flows,
Yeah.
the 8 positions,
Right.
or on each of the cross sections, eight data positions, in other words.
I
So the
see.
8 data positions that I extract, I have to graphically represent them to see
Yes.
how the uh, the sound varies, and then to the deficit or to uh, not the deficit of the sound, for
I
instance.
understand.
Then
Yeah.
if there's cross sections that create a deficit to the sound, I would create out of the 8 layers, which would be one
Mm-hmm.
sound of the composition,
Mm-hmm.
a multiple, say 1, 2, 3, or 4 representations.
Uh-huh.
You
Uh-huh.
see, so
Yes. Yeah.
that's how it's broken down.
I understand. I understand. Another question, and I'm hogging the chat here, but
No,
please
no
help me
problem, no problem.
keep an eye on the
It's a
chat.
bit quiet, so it's okay.
Cool, cool. But you and I, we speak a lot, so this is great for me to just to continue where we left off a day ago.
Yeah.
So when these measurements were taken in this cooling system, the measurements to supply the data for you to generate sound, what was flowing in the pipe in this cooling system? Was it a water or a particular cooling liquid?
Okay, there was water flowing through the pipe originally. Okay, so that created the corrosion. So
Okay.
internal corrosion, as I showed you in the diagram,
Yeah.
where the corrosion goes into the walls of the pipe, or external corrosion. Okay, so there was water flowing through it, and the temperature would, say, from A to Z to the end of the pipe, it would increase in pressure, in temperature, because the system is hot. So it flows from a cool system right through to a point where the temperature increases and then finally goes out of the system. So, in other words, if at that point the temperature was a bit higher than normal, which was the case, then that would indicate that there was a problem in the system.
Uh-huh.
Okay, so they would investigate the problem and see how much corrosion. The first thing is how much corrosion buildup, because as corrosion buildup increases, so does the flow decrease.
Uh-huh. Uh-huh.
Okay, so they had to specifically find where corrosion was detected, and then cut the pipe, because it's an expensive cooling system.
Sure.
And then replace units of the pipe in certain areas. But this whole thing was corroded. So it was
Wait.
time to replace the whole thing, you
I
know.
see.
So it had, like, if I can recall, about 38 different points of corrosion.
Okay.
So they had to replace the whole system. And I was fortunate enough to get from the engineers the statistics and the readings and everything. And then I was away, you know. I converted them into, through MATLAB, into, frequencies, because I initially had the idea of putting frequency through the pipe instead of water flow, and that determined. I don't know if you heard the frequency. I couldn't hear the frequency.
I could.
Okay.
Your examples, your music examples were spot on. I could actually hear that. Yes.
Okay. So that was what happened.
Right. Right. We have a I beg your pardon. We have a question in the chat. Hi Dimitri. It's a very interesting concept. I was wondering from a more practical viewpoint, what kind of software did you use to collect / analyze the data, and then also to generate the sounds?
MATLAB. And to
Cool,
generate the sounds, MATLAB as well.
cool. The collected data you got from engineers who specialize in
Yes.
cooling systems, right?
Yeah.
Mm.
You will see in my notes, in my PDF file on the computer, because these guys, okay, initially were going to use two different systems, we're introducing two different systems. They supplied me with information of the wrong cooling system.
Okay.
So the one that I specifically chatted to you about on the program is the right one. So
Okay.
I haven't had the time to change it on the PDF file, but I will do it in course.
Cool, cool, fantastic. We have another question before I fire
No
off. Hi,
problem.
Dimitri, good to chat. My apologies, I missed a lot of the talk. Is this done through a process of physical modeling, is the question?
Sorry, I missed a lot of the talk. Is this done through process of physical modeling? I would say partly yes, but if you're involved in sound, the way that I'm involved in, it's like beyond that. You know, you diagnose a specific structure, and I gave it to the pharmaceutical department, the complete piece. A lot of them weren't interested, but like, you know, that was my production of
Right,
analysis
right.
versus sound, you know, for instance. So you could say it's a physical modeling piece, yes.
For my, from my perspective, I have been thinking along the lines of the sonification or oralization of data.
Yes.
Um, but hey, I'm not into cooling systems, so I may be
No problem. It's a
completely
sound
wrong.
that goes ee as it detects corrosion, you know.
Right. One more question from my side. Back to the more practicalities of the previous, or the question one before last. When you say you used MATLAB to generate the sounds as well, so MATLAB functions to generate sine waves in real time, or how did you go about it? The actual generating the actual audio output?
Okay, I use two processes, the MATLAB to analyze all the sound, to
Okay,
graphically plot all the intricacies involved
right.
that weren't clear
Yeah.
in, I could have used a sound wave in MATLAB, but MATLAB produced me with a sound wave, and then I took the sound wave and specifically generated it in a Steinberg wavelab,
Ah, okay.
because I
Okay.
think Steinberg wavelab is the most extreme editing system out
Right. Yeah.
for
Good
me.
point. Good point. Yeah. MATLAB's a stunning language for data analysis and for yeah, matrices.
Yeah.
But you're right. At the crux of the matter is we still musicians. You know, we still like to work with music software.
You know what, Theo? In MATLAB, if
Mm.
you look at, for instance, a second, you
Yeah.
can break it down into like various modes before the second, like 0.002 of a second, and that,
Hmm.
and and um, and that was that's the type of precision that I enjoy. You know,
Right.
that you
Right.
can, um, for instance, edit
Mm.
right to 0.2, 0.3, 0.4 of a second.
Yeah, yeah. Your resolution is limited by the 64-bit floating point that
Exactly.
uh, limitation that you work with in MATLAB, which is cool. Yeah, I've always sensed in your work that there was this like a tug of war between using music software which smooths over a lot of stuff to make it sound cool. You know,
Exactly.
the filters in Max MSP sound beautiful, you know, but it's kind of nice to fiddle with a DSP, a toolbox in MATLAB, and yeah, work with data, not necessarily with an audio outcome. That I find that very stimulating in my own work as well.
You
So
see,
we will be
MATLAB
hearing,
gives you a yes and a no. This is how it's done.
yeah,
The analysis is this, and
yeah,
then it's up to you what you do.
right, right,
So I use WaveLab because it's out of all generators versus editing. I use 3 or 4 different types of processes. I found that
right,
is the most advanced
right, right.
and user friendly and hands on.
True. Yeah, yeah, yeah. The interface is very,
Yeah.
how can I say, musician friendly in a way. So we will be hearing the composition in tonight's concert. Is it out on CD? Your work available on CD?
No, I'll tell you what happened. The whole work was designed and for Casper Toplitz in France to perform
Oh,
this on like you could say for 5 strings on a double bass. Why I say double bass? Because it has a convex bridge, so that you can select which strings you want to bow,
right.
rather than a flat string, which a double bass would have. So the whole thing was designed in Avignon because they were building a whole new piping system underground. So it was an underground venture into this echo chamber, you could say.
Right, right.
But then at the last minute, he decided no, he's not going to do it because you must understand, he's an improviser. So for 60 minutes to be like specific on what I created, he says no. So, okay, then I gave it up. It was
Yeah, yeah.
meant to produce, it's
That
a world premiere at
right,
BE 2022.
right. Oh, brilliant, brilliant. Yeah, one can speak at length about the relationship with performers. Sometimes it works very well, very constructive relationship, and sometimes it yeah takes two people with similar visions to engage in this, shall we say, type of music. There's another question in the up to you part. So. Where human decision making kicks in, I think that is what's meant. In this up to you part, were there specific categories of data that informed your creative sonification interpretations of that data?
Uh, no, because I work with data, I'm keen to produce, and not to produce, to showcase another piece of mine next year, which is about highways, the congestion of um, uh, all my analysis is done on congestion and how that breaks up into sporadic protuberances with where cars move away from the congestion and others come to the congestion and that. So I've got an interesting electronic piece for that and a lot of piano pieces, but I'm going to talk a lot about that next year. But Miles, regarding your question, is that no specific data or series of data influenced me. I just analyzed everything and produced the whole basis of the work in about a year, and then started intricate details in between, because that's how I work with data. It's like nothing. you get it on a piece of paper and it means nothing unless you hear it specifically. Only after a year and a half could I really listen to a specific piece and say, okay, this
Yeah.
is what came out of it, and then
Right.
decide, okay, would I use it or wouldn't I use it? And that's how I processed it.
Right. Um, you're talking about a very long gestation process, but tonight we're listening to an excerpt from the work.
Yes,
And this excerpt is approximately 28 minutes in duration. Am I correct?
that's right, Theo.
Right. So the entire work, when it's done, how long do you think it would be?
Okay, the work is completed. It's about 60 minutes.
Wow. Okay.
Okay. So, in other words, the 20 out of the 28 minutes, the first 14 minutes, 14 or 16 minutes, I can't recall very well, is high pitched sound.
Yes.
And then from there on, it's like subharmonic and low
Oh, okay.
pitched sound.
Right.
So,
Right.
okay, the subharmonic, as I said in my explanation of the piece, comes from the inward buildup uh, of corrosion. So it's not
Right.
extending out, it's extending in to the pipe,
Right.
into the
Right.
walls of the pipe, the corrosion. The
Right.
high pitch corrosion is determined from the corrosion that is extending out of the pipe.
Okay.
Two basic elements to visualize.
Okay.
High
Yeah.
uh, the high frequency is due to the extensions out, and low frequencies due to the extensions in to the pipe.
Lovely. Mm.
And you find you'll hear even the bass frequencies are extremely, I had to use extreme um, listening techniques because like they would overflow of each other, and subharmonic
Okay.
frequencies are extremely difficult to hear. The high frequencies
Right.
you can hear, but the
Yeah.
subharmonics are like extremely difficult to control.
Mm. Mm. Yeah. Yeah. Regardless of the musical style, I mean, it's a perennial challenge or universal challenge, I think.
It's
Um,
for me also quite
I have to say,
amazing
mm,
to
yeah, 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 yeah.
produce pieces like that for when everybody says I'm going to produce I've composed this and that and that, not to undermine anyone, but I don't think along those ways. I think along data, along what determines a process. uh, so we have a process of flow from A to Z. What determines it's not what determines that it's not flowing properly, and how can I analyze that determination? It could be a pipe in a cooling system in a car, for instance, in many other um, uh, uh, purposes. But I'm in the pharmaceutical industry, and I happen to get this information from the engineers that were analyzing the sound, and I had to get in 6 months to get first the correct unit that they were using that I had already
Okay.
published incorrectly, and
Okay.
this specific unit uh, um,
Mm, mm,
that they were using, and the data to
mm.
release the data as a composition. It took like heavy negotiation, about 6 months to negotiate. Yes, yes, no, yes, no, filling this form, filling that form, and so forth.
Right. Right. Yeah, indeed. Well, incorrect data, it can happen. It happened to NASA in a Mars mission. Different companies had used text. So, don't worry.
Look, we're not that advanced, but like we're playing with small stuff now. But it's it's very important. It gives people a different aspect to what they could do with sound.
Of course.
You know, so
of course.
you know, basically you could say I could create a melodramatic composition, blah blah blah, using this and that software and this and that type of effect. But like, it doesn't interest me. You know, it interests me more in that field.
Why I insist that you politely insist that you turn to electrons, because you occupy a very, very special position in Southern African or South African composition. Your work is really of crucial importance, and you have to persevere, and you have to keep working, please.
I will, Theo, as much as possible.
Right, right. So I think we're done with the chat questions, and it remains then for me to say, Dimitri, I'd like to repeat, you're a very, very special composer, special musician, and thank you so much for your work over many, many years.
Theo, the other thing is, I didn't study music. I'm a pharmacist, but I feel it's more important to have an obsession about sound than to have studied music. You know, so with all my input from the pharmaceutical side of and the scientific side and the mathematical side, we can create a new field of investigation.
Right. Indeed. And that is a very, very noble cause to pursue. Dimitri, thank you so much for your time, and I'm looking forward tremendously to this evening's concert and to next year's work with you.
Thank you very much, Theo, and thanks, Miles, for giving me your questions. And just listen to the piece and see what you think, and then email me or let me know how you feel. That's basically it, you know.
Will do. Take care.
Thank you. Bye.